All right, ladies and gentlemen, this class recording has started. So, let me adjust this microphone. It's going to sound good on the recording, but that's okay. All right, yesterday, we finished up the outline dealing with conservation of mechanical energy, and then we got into work energy theorem. So the two main points that we want to get out of yesterday's outline. First is, there we go. All right. When there are only conservative forces acting on an object, and we said there were two kinds of conservative forces, gravity and then elasticy, springy, rubber bands, that kind of stuff. When there are only conservative forces acting on an object, mechanical energy is conserved. And we summarize that idea with this equation, MEI equals MEF, where ME stands for mechanical energy, I stands for initial, right? So the initial mechanical energy has to equal the final mechanical energy. Okay? But remember that we talked about mechanical energy being a combination of these three forces, or these three energies, so we can expand this initial equation to be a more detailed version of MEI equals MEF. And this is kind of how we'll start problems, and we'll see that here in just a second. A more detailed version, but we get the same idea. Okay? But this only applies if gravity and springs, elastics, whatever, are the only forces acting on an object. A lot of times, that's not the case. When that's not the case, our analysis of the problem shifts to non-conservative forces. When non-conservative forces do work on a system, mechanical energy is not conserved. So we summarize that with this equation that we call the work energy theorem. What it states is that if we start with a certain amount of mechanical energy, we then do work on that system, W standing for work, the NC standing for non-conservative. So we start with a certain amount of mechanical energy, we do work, and then we end up with a final amount of mechanical energy. The difference between the initial energy and the final energy is how much work we did, because that's what work does. Work changes the energy of an object. Good there. Okay. So let's talk about some of these examples on this sheet that says conservative forces, conservation of mechanical energy, and non-conservative forces, work energy theorem. We are going to start with, hold on one second. We are going to start, sorry everybody, didn't mean to disrupt your educational flow. We are going to start at the top of the page that says conservation of mechanical energy, and we are going to do problem number 1. Okay, ready? Here we go. So problem number 1 says, a 1 kilogram ball, originally at rest, falls off of a table that is 0.70 meters high. So 2 parts. Part A, how much kinetic energy does the ball have just before it hits the floor? And then B, what is the speed just before it hits the floor? So, let's start with part A. First step in this process. First thing we should do before we do anything else is what? Any ideas? I like to start in a certain spot, and I want you guys to start in that spot too. Not that it's the only way to do these problems, but I think this is the best way to start. Where should we start? What's the first thing we should do? Any ideas? I know normally we don't talk like even when the whole class is here, but when there's only like 12 of you, it's really awkward. So, So, what should we do first? Kate, even before we do that, I think we should start somewhere else. Because what formula are we writing, Kate? Why would we write the kinetic energy formula? So in part A, it's asking us to find how much kinetic energy, right? So really, the first thing I think we should do is identify what it is that we're looking for. Because ultimately, we need to make a plan to get to what we're looking for. But if we don't know where we're going, we can't make a plan to get there. So let's first identify whatever it is that we're looking for. So in part A, we know that we're looking for kinetic energy. If we're looking for kinetic energy just before it hits the floor, what part of the problem are we dealing with? The beginning part of the problem or the ending part of the problem? The end. So really, we're looking for the final kinetic energy, right? How much kinetic energy does it have at the end of this problem? Right? Just before it hits the floor. Because after it hits the floor, that's something different. But just before it hits the floor, we're still good. Okay. We've identified what we're looking for. Where should we go next? What should be the next step of our problem? Or the next step in solving this problem? We've identified what we're looking for. Right? Selma, where should we go next? Before we do that, let's do some other things. This problem has given you a bunch of information, right? Let's start identifying some of that information. So we've identified what we're looking for. Now, what do we have to work with to get to what we're looking for? So what's one thing that this problem information gave us to work with to get to this final answer? What's one thing they told us in the problem? Okay, good. What about the ball? So that's going to be, okay, so that's going to be the mass of the ball, right? We know that. We have that information. What else do we know? What other information did they give us in this problem? Tyler. Okay, so if it's 0.7 meters high, that's going to be a height, right? Okay, but Tyler, which height is that? That's where the ball starts this problem, right? So which height is that, initial or final? That's going to be the initial height of the ball, 0.70 meters, okay? All right, we've taken care of the numbers that they gave us in the problem, but there's a couple more things that we can sort of logically assume, even though they don't specifically say it in the problem. Like what? What else can we logically assume about this ball and its motion, even though it doesn't specifically tell us in the problem? Dolly, go ahead. Okay, so we know that the effective gravity here on Earth, 9.81 meters per second squared. Okay, so that's some information that might come in handy later, right? What other information did they give us? Come on. What else? Just say it. Come on. I know some of you are thinking it. What other information should we give us in this problem? Come on, somebody else besides Kate. She can't answer every question. All right, Kate and Tyler are off limits for the rest of the problem. The rest of you. What other information did they give us in this problem to work with? It's gonna be a long class, right? This is gonna be a great recording, by the way. So, come on. What other things did they tell us? Yes, I know. That's what I'm trying to get you guys off of the cricket noises. All right, Sarah, what's it? Okay. Mechanical energy is a combination of a bunch of stuff, right? Let's go with more literal things that they told us. Matt, what's one other thing they told us in this problem? The final height. Where does this ball end up? On the ground. So what is the final height of the ball going to be in this problem? 0. There we go. See, we do know some things, all right? There's one other thing that this problem tells us, all right, about this ball and its motion, even though it doesn't specifically say it, that we can assume. Kate can't save you guys anymore. Oh, it's actually a question? Yeah. Okay, go ahead, Kate. Right. Okay. First, okay, I'm trying to take us through this process here, right? First, we identified what we were supposed to find out, okay? After we do that, let's get all the information that we can get. Then we'll make a plan for how to get there, okay? So I'm kind of trying to take you through this process here, okay? There's one more piece of information that's in this problem and the description of the problem that might be helpful to us in solving it. One more thing that might be helpful in solving this problem. Jack. Originally at rest. Jack, what is that telling us about? When? What part of the problem? Beginning or end? Beginning. And that means that the initial velocity of this ball is equal to what? Zero. There we go, everybody. See? You can get there. All right. Okay. We've identified what we're looking for. We've identified what information we have to work with, okay? So now, Kate, let's go with making a plan. What is making the ball go from the table to the floor? Gravity. And we learned yesterday, I think you told us, right? Gravity is what kind of a force? Conservative force is gravity. Meaning, what's true about the mechanical energy? It's going to be conserved. And that means that this problem starts off like this. Because that's what conservation of energy means. That the mechanical energy at the beginning equals the mechanical energy at the end. Okay? Good there. Now, we said that we can make a more detailed version of this equation. You don't have to show me this every single step, but because this is our first problem, I'm going to show you it right now. We talked about the idea that when we talk mechanical energy, it's actually a combination of three kinds of energy. So NEI is really KEI plus PEGI plus PEEI, right? And the final mechanical energy is really final mechanical energy is final kinetic energy plus final gravitational potential energy plus final elastic potential energy. These two equations are basically telling you the same thing. The bottom one's just a little more detailed than the top one. Okay, good there. Now, this looks daunting. Lots of letters, lots of terms, lots of subscripts. But it becomes easier if we know something about energy. First, elastic potential energy. Where does elastic potential energy come from? What has to happen before elastic potential energy affects a situation? John. We got to stretch something or we have to compress something. Sean, is anything being stretched or compressed in this problem? No. So that means that we can safely assume that the initial elastic potential energy is zero and the final elastic potential energy is zero as well. Okay? So we've eliminated two terms out of this equation. Okay? Based on the information that we got out of the problem before we even started this, we can eliminate a couple more things from this equation. All right? Jack, what did you tell us about the initial velocity of this ball? It's zero. If the initial velocity of the ball is zero, what else is going to be zero? Nope, not necessarily. Matt, what were you going to say? Not the final kinetic energy. If the initial velocity is zero, the initial kinetic energy will also be zero. Jack, does that make sense? Okay. Kinetic energy depends on speed. If there's no speed, there's no kinetic energy. Right? Matt, you told us what about the height of this ball? The final height is zero. Potential gravitational energy depends on height. If the ball ends up at zero, how much gravitational potential energy will it have at the end of the problem? 0. Okay? Does that make sense? Okay, good. Right. But remember that kinetic energy, so let's look at it first as far as conceptually, right? Kinetic energy is energy of motion, right? Something has to be moving in order to have kinetic energy. If it's not moving at the beginning of the problem because it's originally at rest, it has no kinetic energy, right? If we want to look at it, Kate, if we want to look at it from a formula standpoint, right, there's our formula for kinetic energy. What are we doing on the right-hand side? Mathematically, math operation, what are we doing on the right-hand side? So even if we multiply, if we throw 1 0 anywhere in that equation, the answer is 0. Does that make sense? So yes, mass does play a role, but the energy depends on the mass and the speed. And if there's no speed, there's no energy. Kinetic energy. Okay? Tommy, go ahead.
Wait, so the final gravitational potential energy is 0 because of the time height?
Because gravitational potential energy depends on mass times gravitational acceleration times height, and if the height is 0, the gravitational potential energy is 0. Does that make sense? Yeah. Okay. All right, good there. So now, this equation, again, well, first we made it more detailed, but now we're going to actually make it simpler. Because after we got rid of all the stuff we needed to get rid of, right, because it was 0, this big long equation simplifies down into this. Okay? Does that make sense? So even though mechanical energy is conserved, we don't have a lot of kinds of mechanical energy at certain times in this problem, so we can simplify it down to just this equation. Okay? All right. So that means if we know how much gravitational potential energy something has at the beginning of the problem, we will know how much kinetic energy it has at the end of the problem. Tommy, you just told us that the gravitational potential energy of an object depends on 3 things, right? What does it depend on?
Mass,
the mass, gravitational acceleration, and height. Tommy, if we're talking about the initial gravitational potential energy, which height should we worry about? The initial height. Does that make sense? Going from that step to the next step? Okay. So, do we know the mass of this object? Yeah. Do we know the effective gravity here on Earth? Yeah. Do we know the initial height? Yeah. So now we have all 3 things that we can figure out how much potential energy this object starts with, so that would give us how much kinetic energy it's going to end up with. Plug it into your calculator and figure it out. This is what my calculator gives me, 6.867. Okay, but, is that going to be our final answer? No. 1.0 kilograms has how many sig digs? 2. 9.81 doesn't count. 0.70 has, the first 0 is not significant. So 2, so that means our answer should be 6.9. And our unit is going to be joules. All right, good there. Whew. All right. Okay, part B. Part B says, what is its speed just before it hits the floor? So if it wants to know the speed, okay, so first step in the problem, we should identify what? Well, more generally, what should we identify? Yeah. What's the first thing we should do, Sarah? Okay. What's the first thing we should do? What are we finding, right? What is this question asking us for? So, Sarah, what is this question asking us for? Velocity. When? Right before it hits the floor. Which part of the ball's trip is that? Beginning or end? End. So that means really this question is asking us for the final velocity, right? Things we know. Well, we know the ball is still equal to 1.0 kilograms, right? And we just found out in the previous part of the problem that the final kinetic energy of the ball is 6.9 joules. Good there? All those other things are still true as well, but these are the things that determine kinetic energy. So let's just keep it at this, right? Kate, we just talked about that. How do we figure out the kinetic energy of an object? Velocity squared. And in this case, if we know the final kinetic energy, that would then correspond to the final velocity. Right? So, a couple ways we can go about this now. First, we can plug the numbers into the equation and then solve for VF. The other way we can do it is we can get VF by itself originally, then plug the numbers in at the end. Okay? I'm going to do it the second way. So the first thing I would do is do this. Good. Then I would do this. And then I would do this. Now, we have an equation that has VF by itself on the right-hand side, KE final and mass on the left-hand side. We know both of those things, so we should be able to figure out what the final velocity is. That's what my calculator gave me. Okay? And then, Kate, is that not what your calculator gave you? Sorry. When I plugged this into my calculator, I used my unrounded answer from the previous problem. Okay, so yeah, if you're 3.71, sorry. What'd you get? 3.7? Okay, 148. Sorry, everybody. Okay. I used my unrounded answer when I did my thing. But still, we have to round this to how many sig digs? 2. So our final answer, 3.7, and because it's a speed, meters per second. Good there? All right. Next, let's take a look at question number 4 on that same sheet, that same part. Okay, so question number 4 says, a pendulum bob with a mass of 0.5 kilograms is raised to an unknown height and dropped. When it passes through the lowest position, it is traveling with a speed of 1.9 meters per second. What height was it dropped from? So, first things first, right? How do we start this? Nope. Figure out what we have to get to. Jack, what is this problem asking us for? The height when? The initial height, because it wants to know what height did we drop it from. So that's the initial height. Okay? All right. Now that we've identified what we're looking for, now we write down. Not yet. Well, we know. Matt, what's one thing we know? Okay, it told us that the mass of this pendulum bob, 0.50 kilograms. Okay? What else do we know? Phillips.
Traveling at a speed of 1.9 meters per second.
Traveling at a speed of 1.9 meters per second. Phillips, when does that happen? Whenever it's falling, so at its lowest point. Is that going to be the beginning of its flight or the end of its flight? End. So that means that this velocity is really the final velocity. Okay? What else do we know? These are times we have to start making like some, logical conclusions. Kate, what makes the pendulum go from here to there? Okay, we know that gravity does that, and gravity here on Earth, 9.81 meters per second squared. Okay? What else can we logically assume about this problem? Two more things. Phillips, what does it tell you about that 1.9 meters per second? Where does it happen?
Whenever it's stopped.
What does it tell you in the problem about when that happens? Want somebody to help you?
Yeah.
When does that happen? Matt, go ahead. At its lowest point, right? Matt, what can we assume about the height if it's the lowest point? If it's 0, right? And so that means that the final height is equal to 0 in this problem. Phillips, does that make sense?
Yeah.
Okay. All right. We raised up the pendulum and we let it go. Right when we let it go, what's it doing? Is it moving right before we let it go? If we're just holding it there, it's not moving, right? So what was the initial velocity of this pendulum? Okay. What was that? What you were going to say? Okay. All right. Good there? As we stated before, what makes the pendulum go from here to here? Gravity. Gravity is what kind of a force? Conservative. Meaning, sorry, sir, we're running out of time. So. Meaning we got this going on, right? And, again, you don't have to do this every time, but because this is one of our first times, KE initial plus PEG initial plus PEE initial equals KE final plus PEG final plus PEE final. Right? Does that make sense? Right? How we do that? Okay. But just like we did in the previous problem, a lot of this stuff is going to go away. Right? Sean, is there anything being stretched or compressed in this problem? No. So what does that do to the elastic potential energy in this problem? They're both 0. Okay. Matt, what's the final height of this problem? 0. So what's the final gravitational potential energy? 0. Laura, how did the pendulum start this problem? At 0, it has 0 what? Velocity. What does that do to the initial kinetic energy? It makes it 0 as well. Okay? So again, a bunch of terms in this equation drop out, and we're left with PEG initial equals KE final. Good? Now, the thing we're looking for, the initial height, doesn't show up in this equation as it's written, right? But we know that we calculate the gravitational potential energy according to what? Tommy, what three things do we have to know to calculate the gravitational potential energy?
Height, mass, temperature, acceleration.
And which height are we worried about for this part of the problem, Tommy? Okay. Okay. To calculate the kinetic energy, what do we have to know? And in this case, because we're talking about the ending of this problem, right, we want that. Okay? Good there. All right. Now, we have an equation that has the term that we're trying to solve for in it, so we can solve for it. First thing I'm going to do is I'm going to get the initial height by itself on one side of the equation. To do that, I'm going to do this. Everybody follow that? Is that a no or is that a yeah? Okay. All right. Kate, go ahead. The 1/2 mv squared is really the same as mv squared over 2, right? That's the equivalent way of writing it, yes? So when we bring the mg over to the other side, it's on the bottom with the 2 in that fraction. Is that good, Kate? Is that good? All right. Before we plug anything else in, we can also do something here to make our lives a little easier. Mathematically, what can we do to that right-hand side of the equation? Tommy. Cancel m, right? If we have m on the top and m on the bottom, right? We can just get rid of it. Divides out anyway. Could we plug it into the problem? Sure, we could, but it's going to give us the same answer. Now we have less numbers to worry about. Okay? All right, so now we have H initial equals VF squared over 2G. And we know all those things. So now we can figure out what the initial height of this pendulum was. If you are using your TI graphing calculator, on the bottom of this fraction is 2G. Make sure you use your parentheses properly, right? Don't type in 1.9 squared divided by 2 times G, because it will do the order of operations and you will get the incorrect answer. Make sure you use your parentheses properly. Remember, those are just representative of general variables, but we did here, we have numbers for all of those. Okay, good there. Here's what I want you to do next. We have about 5 minutes left. I want to see if you guys can do question number 2 on your own. Instead of on your own, you can work with the person next to you, okay? I will start doing question number 2 up here on the board, just silently though, all right? I won't explain everything, but I'll go through the process. So go ahead, talk to somebody next to you if you want to. Work on number 2 underneath conservation of mechanical energy. Yes. Did you get, what did you get? Okay, I think I know what you did. Good. So up on the board, I have what I'm looking for and the things I have to work with. Thank you. If you did part A, there's the answer for part B. Alright. For homework tonight, I would like you to try number 5 and number 6 from Conservation of Mechanical Energy. We didn't do any work energy theorem problems, so I won't do those anymore. Okay? Try number 5 and number 6 tonight, homework. I will post the answers on the homework event on the calendar. Okay?